Good evening, Lamai. Okay, today we are going to discuss about the molecular kinetic theory. That is the first discussion for today. Right? So, what is this? This molecular kinetic theory. So, you may have heard about this thing. Yes, you have heard about this thing, right? At the first class, when we are introducing the ideal gases to you, right? So, those assumptions, those 5 assumptions of ideal gases came from this theory, the molecular kinetic theory, right? You remember that? Right. Okay. So, today we are going to discuss about the equation of the molecular kinetic theory, which is actually related to the gases, right? And then we will discuss some derivations coming from that equation and we will proceed, right? Okay, let's start with the equation of molecular kinetic theory, which is related to the gases, right? The equations look like this. PV, the pressure and the volume, that multiplication is equal to, right, 1/3 m dash capital N C squared bar, right? This is the equation of molecular kinetic theory, which is related to the gases, right? So, the PV comes up with the normal meanings, right? The pressure of the gas and the volume of the gas, and this m, right? So, I written it as m dash. Actually, it represent, this m represent the mass of a molecule, the mass of a gas molecule, mass of a one molecule, right? Mass of a one molecule, mass of one molecule, mass of a molecule, right? And this N, this capital N, is actually giving you the number of molecules, number of gas molecules, right? And this C squared bar actually representing the mean square speed. Mean square speed. We'll discuss more about that thing, right? A new term, no? Mean square speed. Mean square speed. Mean square speed. Right? Okay. Actually, when it comes to this multiplication, the mass of a molecule and the number of gas molecules will actually giving you the total mass of your gas. This will give you the total mass of your gas, which is actually m, right? It is the total mass of the gas. The idea is like this, Norman. Just think of a system like this, gas system, with let's say 5 gas molecules, right? And consider the mass of one molecule. The mass of one molecule is equal to 5 micrograms. Just a simple number, right? Mass of one molecule is 5 micrograms. So, all the molecules are with 5 micrograms mass, right? So, your m dash is actually 5 micrograms. This is the idea, right? Mass of a molecule is 5 micrograms. Then, what is the mass of whole gas? The mass of whole gas. If we are regarding it as m, that mass of whole gas is going to be then mass of a molecule into number of gas molecules, that is 1, 2, 3, 4, 5. So, mass of the whole gas is equal to 25 micrograms in the system. That is a simple idea. Mass of one molecule into number of gas molecules. Mass of one molecule into number of gas molecules will give you the mass of the whole system, whole gas, right? So that is the idea. So this is your molecular kinetic equation, right? This is referred to as the molecular kinetic equation. Or the equation of the molecular kinetic theory, which is related to gases. Right? We'll discuss about the C squared bar later, right? What that means. So this is the idea. Clear? Right? Those things are appearing in your note, right? Okay. What is the importance of learning this thing? What is the importance of learning this molecular kinetic equation? Let's discuss that thing. Actually, this molecular kinetic equation provides you some idea about pressure, right? So some special idea about pressure. What is that? Actually, if you have to examine this molecular kinetic equation, right, we will come across the factors affecting the pressure, the molecular factors which will affect the pressure of a gas. See, what are those? So if you subject this P, if you subject this pressure of this equation, let's subject this pressure of this equation. So P is going to be then equal to 1/3 m dash, right, in, I'll take that V to here, I'll take that V to here, so that NOV C squared bar, right? So this is pressure. Basically, when looking at this thing, you clearly see the pressure is proportional to m dash, mass of molecule. The pressure is proportional to NOV, which will be the concentration of molecules. Concentration of molecules, number of molecules in a unit volume. Number of molecules in unit volume, that is representing you the concentration, right? And C squared bar, it is something about speeds. So pressure is proportional to speed. That is what this says, right? If you subject pressure, you will come up with this kind of a relationship, right? So when we are looking at this thing, we can say when the mass increases, pressure increases. Mass of molecule increases, pressure increases. When the concentration of molecules increase, pressure increases. When the speed of molecules increase, pressure increase, right? That is the idea here. So do you feel that thing? Even though the equation says like that, do you feel that when the mass of molecule increases, the pressure increases? Do you feel that? Let's discuss about that thing, right? It is like this, no? It is like this. So I'll draw the picture here, the mass effect, right? So let's say you have a gas like this. In this vessel, you are with a gas, right? See, these are your gas molecules, right? So what is pressure? What is pressure? The pressure is actually the force exerted by these gas molecules on the walls of the container in unit volume. The pressure is that, no? P is equal to force over area, right? So pressure is the force exerted by these gas molecules when they hit the walls in a unit volume. Force for unit volume. Force exerted by the gas molecules when they hit the walls in a unit volume, per unit volume. That is the pressure of the gas, right? Then what is this force means? Force means that is the delta mv over time. The force is actually, right, change in momentum per unit time. Force is change in momentum per unit time, right? That is force, no? Force is actually change in momentum per unit time, right? If the mass of a particle is high, if you are with a greater mass with these particles, if you are with greater mass with these particles, the change of momentum when these guys hit the walls will be high. Why? When the m is high, right? Definitely delta mv will be high, right? So when you are with a greater mass with your gas particles, when they hit those walls of the container, they will exert a greater pressure. They will exert a greater force that leads to a greater pressure, right? That is the mass effect. Greater the mass, greater will be the force exerted on walls, and greater will be the pressure then. Right? That is what this equation says. When the m is high, pressure is high, right? Okay. Let's discuss about the second idea. How this N over V, or the concentration of volume, concentration of molecules, affect the pressure. The idea is this, right? Just think of this kind of situation, right? Two gaseous systems, where you have very less molecular concentration and where you are with a greater molecular concentration. Greater concentration means in a unit volume you have more number of molecules, right? Here the N over V, the concentration or the number of molecules in a unit volume is low. At here number of molecules per unit volume is high, right? Then in a considering instance, when one particle hit the walls of this container, right? Not one particle but few particles will hit the walls of the container with this kind of system. With this kind of system, more collisions will occur with the walls of the container compared to a situation with a less concentration. The concentration is low. Here the concentration is high. So with a system with more number of molecules in unit volume, more particles will collide with the walls of the container compared to a system with a lesser concentration. So that more particle collisions will lead to a greater force on the walls of the container in unit volume compared to this kind of a situation with low concentration. So more the number of molecules, more force will be exerted on the walls of the container. That means more pressure will be exerted on the walls of the container, so that the pressure will be high with this system compared to here. So when the N over V, or the concentration, increases, the pressure will increase. That is the second factor which will affect the pressure of a gas according to the molecular kinetic equation, according to molecular kinetic theory, right? The third thing is the speed of gas molecules. This means core speed, the mean values representing normally the rational values, right? We can take for speeds, those are the mean values, right? Mean values representing some value, some general value for all the system. That is what means does, no? Right? Taking a mean means, right, you are taking some acceptable value, some general value to represent all the guys, right? That is the idea. So the mean speed, the speed of molecules, right? Let's concern about that thing, how that affect. to the pressure, speed of molecules. Actually, in this case, you clearly see the speed of molecules squared, right? It is kind of a squared term. So basically, one can write it as like this: speed of molecule into speed of molecule, right? Speed of molecule twice. Speed of molecule twice. That is what it says, right? C squared bar means, right? Speed of molecules. Those terms appear twice, right? That's the idea. That is what it says, right? So actually, speed of molecules affect the pressure in two ways. That is why the power is there, twice is there, right? What are the two methods? That are the two ways that speed of molecules will affect the pressure. Speed of molecules will increase the pressure, right? It's like this. Let's examine the two ways, right? Let's concern these two systems, right? Let's concern these two systems. Right? I'll take, right? So let's say with these guys, the speed of molecules is actually, right, 1 ms minus 1, low value, and with these guys, speed of molecules equals 100 ms minus 1. Let's see. So what will happen? These particles move slowly. These particles move slowly. So you need time. You need time, right? Only 1 or 2 particles will hit the walls, as they are moving slowly. No? So you need time. Only 1 or 2 molecules will hit the walls. But as these guys are moving very speedy motions are there, you need time, in a considering need time, few of the molecules, more than few molecules will hit the walls, right? So more collisions with walls happens with a system with molecules with greater speed than a system with molecules with smaller speeds. So these particles are moving very slowly, like this, very slowly going there and here and there. So you need time, very less number of collisions with the walls of the container. But these particles are moving very fast, like this, very fast. So that more number of collisions can be seen in unit time. So more number of collisions with the walls means more force will exert on the walls. That means pressure will be high. So when the speeds of molecules are greater, more collisions with the walls in a constrained time, and more force will exert and the pressure will be high, right? That is one thing. That is one way of affecting the speed, one way of affecting the pressure by speed. The second way is, even though you are thinking of one single collision of a gas molecule, still the delta MV will be high with this one, as the V is high. So force will be high by these guys exerting on walls. But here delta MV will be low as the speeds are there. So force exerting by one single particle is low, right? So less force exerted means less pressure will be here. Here force exerted by even one single particle is high with greater velocities, greater speeds. So the pressure will be high here, right? So that is how the speed of molecules affect the pressure, the two methods. Because the first thing is more number of collisions are possible in a constrained time interval. So more force will be exerted with the system with greater speeds of molecules. So greater pressure will arise, right? The second thing is, actually more force will be exerted by even single collision if your speed is high, because when the speed is high, momentum change is high, so more force will be exerted on walls even by a single collision, so that will lead you to greater pressure, right now. So that is how the speed of molecules affect the pressure, right? That is why this power is there. It will affect twice, will increase the pressure twice, 2 times, right, when increasing the speeds, right? Okay, that is clear. So just go to the note, Lama, see what they are saying at the note. You have to go through the note, right, from the beginning. You have the equation of molecular kinetic theory, right? All the terms are defined, right? Here the m dash in is the mass of the gas, right? So total mass of the gas, right? Okay. Then this equation gives pressure a macroscopic property in terms of molecular motion, right? Pressure is kind of a macroscopic property, right? What is the macroscopic property means? Macroscopic property means if a property is defined considering the whole system. If a property is defined considering the whole system, such properties are referred to as macroscopic properties. The pressure of the gas is a macroscopic property, right? It is defined, right, concerning the whole system. The volume of the gas, it is a macroscopic property. Considering total system, you define the volume of the gas. The temperature of the gas, right, that is defined concerning the total system, total vessel containing the gas. The number of moles of gas concerning the total system, total vessel which is with the gas is concerned when coming up with the number of moles of the gas there. So those are referred to as bulk properties or the macroscopic properties, right? So the other kind of properties are actually the microscopic properties. Microscopic properties are defined concerning one single molecule, like mass of a molecule, volume of a molecule, which is actually negligible, right? Volume of a molecule, mass of a molecule, speed of one single molecule, which can't be measured anyway, speed of one single molecule, right? Those are microscopic properties. So these things represent kind of that some rationalized value, so some acceptable value to represent speed of one single molecule. We'll discuss this thing later, right, at the next topic, right, what this means actually, right? It is giving you such kind of idea, some acceptable value for, right, the speeds of molecules, one single molecule, right? So this equation explains the pressure, which is a bulk property of a gas, in terms of microscopic properties. Pressure is a macroscopic or bulk property that is defined in terms of microscopic properties. So mass of a gas molecule is a microscopic property. Total mass is a bulk property, macroscopic property. Mass of one single molecule is a microscopic property defined concerning only a single molecule, right? Okay, so that is what it says, right? This equation gives pressure a macroscopic property in terms of molecular motion, molecular properties, right? Significance of this equation is that the pressure is proportional to, they are saying, mass of a molecule, concentration of molecules, as well as mean square speed of molecules. The ideas are clear now? Right. Now let's discuss about this new term, the C squared bar, how that thing came to this picture, right? Okay, right, let's discuss about that thing as well, right? Right, C squared bar. So Lamai, when it comes to gases, three methods of defining speeds of those gas molecules, right? In this section we will discuss three methods of defining molecular speeds. In this section, we will discuss about 3 methods of defining molecular speeds. The first method, right, there is the average speed. The average speed. Average speed. Normally, the averages are defined by C bar. Bar. The average speed. Average speed. The second thing we are going to discuss is actually mean square speed. Mean square speed. Mean square speed. That is what appears here. Mean square speed. Third kind of speeds we will discuss here is root mean square speed, right? Okay, root mean square speed. Root mean square speed. Those are the 3 kinds of molecular speeds we are going to discuss now. Those are things we should know when it comes to A levels, right? Let's come up with a clear idea about these 3 kinds of speeds, right? Let's consider you have a gas like this. You have a gas system like this, right? And let's say that gas contains 5 gas molecules. That gas contains 5 gas molecules. And consider their speeds are like this, right? These are going here and there, right? Let's assume their speeds are like 2 ms minus 1. This guy also going with 2 ms minus 1. This guy going up with 3 ms minus 1. And some 5 ms minus 1 from this guy. And some 10 ms minus 1. Sorry, 8 ms minus 1 from this guy. These are traveling with those speeds. We know that the gas molecules are traveling with various speeds, right? We have learned that thing, right, when we are defining the ideal gases, right? Okay. Random motions with different speeds towards different directions. That is how the gas molecules move, right? Okay. Let's first discuss about the average speed, the concept of average speed. So actually, how to get an average? How to get an average from any kind of a population? How to get an average, right? Let's say for 3 subjects, let's say you are with these kind of marks, 70, 60, right? 70, 60, 70, 65 and, right? You are with 55, 45. Let's say for chemistry you are getting 60 marks. Let's say you are for maths you are getting 65 marks, and for physics you are with 45 marks. Let's see. So what is the average of your mark? What is the average? How to get the average? Basically, the average can be taken by taking the summation of all the entities. That means 70 plus 65 plus 45, taking summation of all the entities and dividing that thing by the number of entities. Number of entities. So number of entities is 3. 1, 2, 3. 3 entities are there. So this value coming up with 180 divided by 3. So the average is 60. Average of the mean value is 60. Right? That is what this is. So take coming up with the averages like this. First add all the numerical values, all the entities, and divide that number by the number of entities. Here 2 entities are there. Right? That is how we are supposed to get an average, right? Okay. So so average value, right, may or may not be there as original value, right? So average is 60, right? But you won't see the 60 appearing here, right? So average is the value, right, which represent which can be represented as a general for all of these three stuff, right? Some rationalized value, right, for these three guys, right? As average, you are getting 60 marks per subject. That is the idea, right? Okay. So with these kind of a population with different numbers, taking the average will give you some idea, right, about your knowledge here, right? Okay. Right. So like this, let's take the average of these speeds as well. So how to get the average of these speeds, right? So first you have to get the summation of all the entities. So let's take the summation. So it is going to be 2 ms minus 1, 2 ms minus 1, 2, 2 and 3 ms minus 1 plus 5 ms minus 1 and 18 ms minus 1, right? That is the summation. You can summation of entities and divide that thing by the total number of entities. You have 1, 2, 3, 4, 5. 5 entities are there. So here 5 things are there, right? That is how we are supposed to get the average, right? So if you have to add these things, you will get some value like 4, 7, 12, 20 divided by 5 is 4. 4 ms minus 1 as your average value. That is how you are expected to come up with an average, right? So the simple idea is that don't worry that much about the symbols they have used, right? So in your note, it is represented as C1 plus C2 plus C3 plus until the Cn divided by the n. What was that actually? The C1 is the speed of the first particle, C2 is the speed of second molecule, C3 is the speed of third molecule. Like that, you have to add up until you cover all the number of molecules. Let's say you are with n number of molecules. So the equation looks like C1 plus C2 plus C3 till you go until the nth number of molecules. The speeds should be summed up and you have to divide that thing with number of molecules, that is n, right? In this case, number of molecules is 5, right? So that is how you are supposed to come up with the average speed. The idea is simple as that, right? So this one, the second kind of speed we are discussing is actually mean square speed. Mean square speed. Mean square speed. How to get the mean square speed? So it is like this. First, take the square value. First, take the square value of each and every speeds and take the mean. So what are the square values of these things? The square values. So 2 to the power square for this one. For this one, it is again 2 to the power square plus for this one is 3 to the power square. Square values of all the speeds of the particles, 5 to the power square plus then you have 8 to the power square. Take the square values. This is square values, right? These are the square values, right? Sorry, these are the square values, right? Take the square values of all the entities and take the square values. That is what I have done, and take the average of that thing. Take the average of that thing. Take the average of that thing. So how to get the average? To get the average, you need to add up all the entities, and then you have to divide that thing with number of entities. Then you have 1, 2, 3, 4, 5. Right? That is how you are supposed to come up with the mean square speed. First, take the square value of all entities and then take the average. To take the average, what you need to do is you have to just sum up all the entities, the values of all the entities, and divide by the number of entities. Here it is 5. Right? So this is the how you are supposed to get the mean square speed. So if you symbolize these things, you can say C1 squared, C2 squared, C3 squared, like until the nth molecule, you can take the squared value of the speeds and divide by the number of molecules, that is n. Right? That is what they have written there. in symbolized form, right? Don't think much about that, right? So these values actually coming up as m squared minus s squared, right? M squared s minus 2, right? Sorry, m squared s minus 2. The unit is like that, right? Square values, no? Squared of this thing then, right? Okay. But that is how we are supposed to come up with the mean square speed. So what would be the value like that? For this mean square speed, you will come up with some greater value. You have 4 here, 4, that is 8, and some 9 here, 17, some 25 here, 17 and 25, 42, some 64 here, no? 64, right? 64 here, so that is 106, no? 106 divided by 5, right? So 106 divided by 5 is going to be 21.2, and that is going to be 21.2. M squared is minus 2. Right? That is all about mean square speed. That is what appearing here. Actually, mean square speed is the squared value of this thing, right? Mean square speed is the squared value of this thing, right? Mean square speed is the squared value of this thing. It is not the squared value of this thing, right? Remember that. The square value of this thing will give you 16, should give you 16, but that is not the value, right? Mean square speed is not the square value of this thing, right? Mean square speed is the square value of this thing. If you have to take the square value of this thing, this square root will cancel off, giving you this, right? Okay. So this is referred to as the root mean square speed. The root mean square speed. See, the root mean square speed. How to get that value? First take the square values. First take the square values. So those are the 2 square, and 3 square. The square value of speeds, 5 square and 8 square. Those are the square values for these speeds. And take the mean of that thing. Take the mean of that thing. First take the square value of those things like this, and take the mean of that thing. Taking the mean means you have to add those entities. And then you have to divide the thing with number of entities, that is 5, right? Okay, things like this. Then this is the c squared bar, and then take the square root, then take the square root of that thing. Take the square root of that thing, right? Taking the square root of the thing, right? So taking the square root, right? Okay, that is the root mean square speed. So if you have to get the ultimate value here, it will be the square root of 21.2. This whole stuff is still there, right? Square root of 21.2, that will be something in between 4 and 5. The 16 is the squared value of 4, 25 is the squared value of 5. So this value resides something between 4 and 5. So that will be some value, some 4-point value, some 4-point value, right? I just put it as like this, right? Some 4-point value, greater than 4, less than 5, right? So this is kind of an acceptable value for gas molecules as their speeds. Some general value for all the gas molecules as their speeds. That is not the true value, right? But some acceptable value which can represent as speeds of gas molecules, right? The gas molecules are moving in different speeds, right? So this is not the true value, right? But some acceptable value to represent the speeds of the gas molecules, right? Okay. Right. So those are the 3 kinds of speeds we should know when it comes to gaseous things. at T levels, right? So just go to the note there. Now see, are you clear with that? Definition of molecular speeds. When n number of molecules in a constant volume container at constant temperature travel with the different speed C1, C2, C3 like Cn, like this kind of system, right? Okay. Different kinds of molecular speeds can be written as, so this is the average speed, taking the average of these speed values, and the mean square speed, right, taking the square values and taking the mean of that, right, and finally root mean square speed, right, taking the square values and the mean, then the square root of the stuff, right. Okay, so those are the three types of molecular speeds, right, we should know when we have to study the A levels, right. Okay, that is clear, right. So let's go towards the next topic. That is a very important topic we are leading up to. Let's move towards that, right. Now Lamai, we are going to derive some relationships. We are now going to come up with some relationships, right, for two important terms with the use of the molecular kinetic equation as well as the PV equals nRT, our ideal gas law, right. That is what we are going to do now. We are going to derive two relationships for two important parameters with the use of molecular kinetic equation as well as the ideal gas law, right. Under that, first let's try to derive an equation for the root mean square speed or for the mean square speed, right. Let's first come up with that, right. Deriving an expression for mean square speed. What is that? That is c squared bar, mean square speed, right. Let's try to derive an expression for this thing. Now this section is frequently asked, right, in your term test papers, in the second term test papers, which is the term test just after the studying of gas laws, right. And the second term test paper, definitely one of these two derivations will be asked. So study these things and you should be able to derive the stuff, right. Okay, so let's go to this derivation, right. So it's like this, Lama. So we know according to ideal gas law, your PV is equal to nRT is the ideal gas law. And then we just learned that PV is also equal to 1/3 of m dash in c squared bar. That is what? That is our molecular kinetic equation. Right? So we clearly see this term as well as this term, both the terms are equal to PV multiplication, right. So that instead of PV here, you can substitute 1/3 of m in c squared bar, because that PV is equal to 1/3 of m in c squared bar. So instead of PV here, you substitute this value. So we'll come up with 1/3 of m dash in c squared bar as nRT. just substituting this value instead of PV here at the ideal gas law, right? And then we know that this multiplication m dash n, this multiplication actually representing the mass of gas, total mass of gas. So we can write this thing as 1/3 m, this simple m, the mass of gas. This is m dash, right? This is the mass of a molecule. Mass of a molecule into number of molecules is equal to mass of the whole gas. Simple m. C squared bar is equal to nRT. If you subject this C squared bar, it will look like this 3 comes there, so 3 nRT and m comes down. I can put it like this, right? But we know that the capital M, molecular weight is equal to right, number of moles, sorry, the mass divided by the number of moles. Molecular weight is equal to G term divided by the mole term, G mole minus 1. This is the molecular weight. G mole minus 1 thing comes up with G thing divided by mole thing, right? This is what happens, right? So actually NOM is the reciprocal of this thing. NOM is the reciprocal of this thing. That means NOM is equal to 1 OM. NOM is equal to 1 OM. So that we can write this thing like C squared bar, right? I'll write it. Yeah, you can write it. C squared bar is equal to 3 RT over M, right? Instead of 1 OM, I just put the, sorry, instead of N over M, I just put the 1 OM, right? So this is the expression for the C squared bar, right? Expression of the C squared bar. I think it's clear, right? So C squared bar is equal to 3 RT over M. 3 RT over M. Right? So let's examine this thing furthermore. I'll give you some time to write these things, right? But before that, first examine, right, the importance of this equation, right? So actually, if you are thinking of the square root of that thing, that is also can be written from this one, right? We'll write that thing as well, right? So the square root of that thing, right? So this is proportional to, so that is equal to 3 RT over M square root, right? Both forms can be asked, right? Actually both are same, right? Just take in the square root. Right. So let's discuss about the importance of this equation, this final relationships, the importance, right? Special note. The importance of these two things. Now, actually, these are the fundamental equations for C squared bar as well as root mean square speed. These are the fundamental equations, the fundamentals, the basics of the root mean square speed as well as the mean square speed. That means, according to this equation, the C squared bar depends only on the temperature and the molecular weight. C squared bar depends only on the temperature and the molecular weight. As the 3 and R are constants, the C squared bar depending is only on the temperature and the molecular weight. Actually, molecular weight means the kind of gas. Molecular weight means the kind of gas. If this capital M is appearing in any equation, that actually represents you the kind of gas. When the kind of gas changes, the molecular weight changes. If your gas is N2, the molecular weight is 28, 14 into 2. No? If your gas is O2, the molecular weight is 32, like that. If it is H2, your molecular weight is 2, like that, right? Neon, you can have 20 as the G mole minus from molecular weight, right? With the type of gas or the kind of gas, the molecular weight will vary. So, if some M term, the capital M term appears in an equation, that says that parameter is varying with the kind of gas, right? The idea is clear. So, C squared bar depends only on the temperature and the kind of gas. Temperature and the kind of gas. Right? This can be taken as absolute temperature and the kind of gas. The Kelvin temperature, right? So, let's write that thing. So, the first important stuff to learn here is the C squared bar means cos speed, and this thing as well, C squared bar the square root, depend only on the temperature and the kind of gas. And kind of gas. Right? That means when temperature increases, your mean square speed will increase, right? When temperature increases, your mean square speed will increase. So, there is kind of a direct relationship as well as the root mean square speed, right? Anyway, those are coming up with some direct relationship, the T and the C squared bar. So, when temperature increases, mean square speed will increase, right? What about the capital M? So, basically the mean square speed will increase only when the M decreases. When the M decreases only, the mean square speed will increase, right? So, when the molecular weight of your considering gas decreases, your root mean square speed will be high. Mean square speed or the root mean square speed will be high when the molecular weight decreases, right? As those guys are with some inverse relationship, right? So, we can say in molecular weight decreases, right? Your mean square speed increases, right? The idea is clear, right? This is very important, no? It's very important. The first point to note, right? I'll put it as the note number 1, the first thing to note with these two relationships, right? The second thing, the most important second thing you should note by these equations is actually, I earlier said that these are the fundamental equations, the basic equations, the fundamentals, right? Equations for c squared bar as well as the root mean c squared bar, right? Root means cos beta. That means the c squared bar as well as the root means cos beta only depends on the temperature and the kind of gas. Temperature and the kind of gas, right? So, according to these equations, remember that this c squared bar and the root means cos beta won't depend on the pressure, won't depend on the volume, as long as you are keeping the temperature and the kind of gas constant. As long as you are keeping the temperature and the kind of gas constant, the c squared bar won't depend on the pressure or the volume. That is very important point, right? Because one may think by just looking at the molecular kinetic equation, one may think when the c squared bar increases, the P will increase, so V will increase. Or one may think when the P increases, C squared bar should increase. One may think like that. It's a false idea. One may think when the volume changes, C squared bar should change. No, that won't occur as long as you are dealing with the same temperature as well as the same gas. This is what this equation says. First write that thing, and after that we'll discuss why the earlier statement is false. Right? Okay. The second point is as long as, sorry, I write it with the other color, right? As long as T and kind of gas are not changing, C squared bar won't depend on the pressure or volume. C squared bar won't change in case of a pressure or volume change. This is very important. Won't change. C squared bar won't change. In case of a pressure or volume change. Right? See, how come? Let's discuss how come that is possible. The point is this: even though it looks like the C squared bar is depending on the pressure and the volume from this molecular kinetic equation, remember that that is not the fundamental equation for the C squared bar, which defined in the C squared bar. The molecular kinetic equation is not the equation which defines the C squared bar. Right? Molecular kinetic equation just get the help of C squared bar to come up with this equality. Molecular kinetic equation just got the help of the C squared bar to come up with that relationship. But that is not the equation which defines the C squared bar. The equation which defines the C squared bar is this. The fundamental of the C squared bar. Fundamental equation, right? So let's see what happens here. So the thing is, as long as you are keeping the temperature constant with the same kind of a gas, as long as you are dealing with the temperature constant with the same kind of gas, this nRT, the nRT term is going to be a constant. As long as, right, the temperature is kept constant with the same kind of gas, this nRT term is going to be a constant for a given gaseous system. For a given gaseous system, nRT term is going to be a constant. If the nRT is a constant, PV should be a constant. If the nRT is constant like that, PV should be a constant. So that the same PV appears here, PV should be a constant. If you increase the pressure, definitely volume will decrease to keep this thing a constant. Its temperature and the kind of gas is not changing. If the temperature and the kind of gas is not changing, if you increase the pressure, to keep this PV a constant, the V will decrease. That is how the things will be managed. So that will be a constant, that means this side will be a constant, that means C squared bar is not going to change. C squared bar is not going to change. Right? So that is how we explain the scenario there. The pressure and the volume changes won't affect the C squared bar as long as the temperature and the kind of gas are kept constant. Right now? The idea is clear? Right. So let's come up with some examples there. Let's write an example here. So I'll write an example here for these two ideas. Right? I'll write an example here. Right? So this is a good example, giving you the idea. Right? Okay, it's like this. So let's take these two guys. Right? So I'll write the examples here, no? I'll write some examples here, right? So after this, go to this, right? Some examples. Okay, just concern this. So you are with, right, some N2 gas, right, N2 gas at 5 atm pressure, and let's say you are at 300 Kelvin temperature. And if you consider this thing with this kind of system, some N2 gas at 10 atm pressure, right? So I'll write it here. So we have some space now. So we'll discuss Lamai. First of all, just copy these things out. First, just copy these things out. Then I'll give you some examples, right? So that's better, no? So just copy the things here. right? Ne? Okay, so we'll come up with some examples here. We'll come up with some examples here for this special knot. Right, some examples. Right, let's compare these things. Say you are with some N2 gas at 5 atm pressure at 300 Kelvin temperature, and you are supposed to compare the C squared bar value of this thing with this kind of system, where again the N2 gas is appearing with 10 atm system at 300 Kelvin. Right, so actually no need to worry about these pressure things, right? What we need to concern is actually the kind of gas and the temperature here. So you clearly see the kind of gas is same with these two occasions. The kind of gas is same. Both the systems are with N2 gas, and both the systems are with 300 Kelvin temperature. Both systems are with 300 Kelvin temperature. As long as the kind of gas and the temperature kept constant, the C squared bar won't change. C squared bar won't change. So with these two systems, the C squared bar values will be equal. Right now? So let's come up with another example. Another example. Let's concern some C squared bar, right, for N2 gas at 10 atm and at 300 Kelvin with a system with some other gas, let's say the same N2 gas, but just 2 atm pressure and some 600 Kelvin is there. Let's compare the C squared bar values of these two systems. So our concern should be just only the kind of gas, both are the same kind of gas, and the temperature. Those are the only stuff we need to concern. So the kind of gas is same, but the temperature here is high. So when the temperature increases, your C squared bar increases, no? The equation is, you remember the equation, C squared bar equation, 3RT over M, no? The relationship with the temperature, right? So when the temperature increases, C squared bar increases, right? So that this system is the greater C squared bar value than here. Clear, no? Right. Let's come up with another example for these points. Right? See, C squared bar is concerned two gases for N2 gas at let's say some volume, right, 5 liter volume, and at 300 Kelvin. Let's compare this stuff with some system with O2 gas at 10 decimeter cubes volume and say at 300 Kelvin temperature. Let's try to compare these two guys. So our concern should be just about the kind of gas as well as the temperature. Kind of gas as well as temperature. So with these two systems, the temperature kept constant. Temperature kept constant, but the kind of gas changes. Kind of gas changes definitely, so that C squared bar will change. C squared bar will change. So how come? Right? What would be the variation there? So the variation says, right? Variation says when the molecular weight increases, C squared bar decreases. When the molecular weight increases, the C squared bar decreases. When the temperature kept constant, right? When the temperature kept constant. So with the system with greater molecular weight, you should observe the smaller C squared bar. So the system with greater molecular weight, this one. The O2, the molecular weight is 32. For N2, the molecular weight is 28. The system with greater molecular weight should come up with a smaller C squared bar. Smaller. Right? This is how we are supposed to apply the things what we have learned with these equations. Right? The thing is clear. So now just copy this thing. This one. Right. So that is all about the C squared bar, the relationship of C squared bar, the fundamental equation of C squared bar, which is the 3RTOM. Right? Okay. So let's move to the next derivation. So at the beginning of the lesson, I have told you we are going to come up with two relationships. One is for the root mean square speed, and the second relationship is for the average kinetic energy. The second relationship is for the average kinetic energy. So actually we know that the equation for the average kinetic energy, that is going to be actually 3 by 2 kBT or 3 by 2 RT per mole of molecules. But that equation is given to you when we are introducing the ideal gases, right? So at the first day of our class about this lesson, right? So we had to introduce that equation saying that the average kinetic energy depends only on the absolute temperature. With that statement, I had given you that equation, the average kinetic energy equation, right? Let's try to derive that thing with the use of molecular kinetic equation as well as the Picos similarity, the ideal gas law. Let's derive that thing. Now we are going to derive an expression for average kinetic energy. For average kinetic energy. Average kinetic energy. Let's do the stuff. Right? This derivation is also, the first part of this derivation is also like the same as the derivation of the C squared bar. Right? Let's start with that, right? So first we can take the PV equals in RD right? So I'll write from here, right? So it's a space now, I'll write it here. So let's start with the PV because NRD. This is the ideal gas law. Then we can come up with the PV equals 1/3 m dash in C squared bar. That is the molecular kinetic equation. Right? As we know that both the equations carry PV, the things are equal. So instead of this PV here, you can write the 1/3 m in C squared bar here, right? So 1/3 m dash in C squared bar is equal to nRT, right? So we know that m dash in the mass of a molecule into number of molecules, mass of a molecule into number of molecules will give you the mass of the total gas. These things are still same as the earlier derivation, right? Mass of whole gas, right? So we can write this 1/3 mc squared bar is equal to nRT, right? So the mc squared bar is equal to 3 nRT, right? So with use of this, we can think of the average kinetic energy, right? So before going for the average kinetic energy, first let's think of the kinetic energy, so that we can write the kinetic energy. Kinetic energy, if you take it as, right, EK kinetic energy, the kinetic energy is actually what? The kinetic energy is actually half mv squared, half mv squared. That means if the general value for the velocity is taken as this, right, c, it could be written like this, half mc squared bar. So that is going to be half the value of this thing, that is 3 nRT over 2. 3 nRT over 2. This is the first important relationship we know. Kinetic energy of a gaseous system is equal to 3/2 nRT. 3/2 nRT, right? It's very important derivation, right? So we can write it that thing. So kinetic energy is equal to 3/2. So I'll write it here, it's better, right? So I'll write it here. The kinetic energy of a system is equal to 3/2 nRT. That is first important derivation. But we are not looking for the kinetic energy, right? We are just looking for the average kinetic energy. We are just looking for the average kinetic energy. This is just the kinetic energy, Ke or the Ek or anywhere, right? So kinetic, right? So notice, right? Kinetic energy Ke, okay, anywhere, right? Energy kinetic, right? Okay. Normally write it as Ek, right? Okay. Then what we need is actually average kinetic energy. No? So if you are referring to average kinetic energy, right? If you are referring to the average kinetic energy, I write it here, right? Average kinetic energy, we can symbolize that thing as energy kinetic average, the mean value, right? That can be taken per mole as well as per molecule. If you are regarding per mole, if you are regarding the average kinetic energy per mole, it is actually EK bar, we'll write it per mole, right? Mole is actually kinetic energy divided by number of moles. That is how you are supposed to get the average to. You are supposed to get the average by taking the value divided by number of entities. So taking the sum of the values and divide by number of entities. So per mole means you have to divide by number of moles. Per mole means you have to divide by number of moles. Average kinetic energy per mole. Kinetic energy divided by number of moles. So it will give us the 3 over 2 is there, nRT is there, divided by number of moles, that is n, number of moles is n at the system. So this n will cancel off, ultimately giving you 3 by 2 RT, 3 by 2 RT. That is the average kinetic energy per mole. Right? If you are referring to per molecule, the average kinetic energy per molecule, right? Kinetic energy average per molecule, then you have to divide the kinetic energy by number of molecules. By number of molecules per molecule. Per molecule means you have to divide by number of molecules. So the kinetic energy is 3 by 2 nRT. Number of molecules means number of molecules can be written as number of moles into Avogadro. Number of moles into Avogadro's constant. That will give you the number of molecules. Number of moles into Avogadro's constant will give you the number of molecules. So that this n will cancel off. That n will cancel off. Finally giving you the 3 by 2 RTOL. 3 by 2 RTOL. Where this ROL, where the ROL can be considered as a constant. Where this ROL can be considered as a constant. This R is a universal gas constant. It's a constant, right? In anywhere. Right? The R value appears as 8.314 joules per Kelvin per mole, right? That won't change. It's a universal constant. If you are doing the experiment in Sri Lanka, or if you are doing the experiment in US, or if you are to do the experiment even in space, anywhere inside our universe, right? The R value won't change. Comes up as 8.314 joules per Kelvin per mole. That is why it is referred to as a universal constant. As well as this L value, the Avogadro's constant, is always 6.022 into 10 to the power 23, right? It won't change depending on the place you are doing the experiment. You can do the experiment in space, you can do the experiment in Sri Lanka, you can do the experiment even under water, deep in the sea. Still the L value is still the same, the 6.022 into 10 to the power 23. That won't change. Those are constant values. Universal constants, right? So constant divided by constant, always giving you a constant. So ROL, that is also a constant, and it is referred to as the Boltzmann constant. Boltzmann constant. So this will be simplified as 302 instead of ROL, instead of this ROL, I just apply the Boltzmann constant. ROL means the Boltzmann constant, Kb into T. Right? Those are the two equations for the average kinetic energy per mole as well as per molecule. right? Here the Boltzmann constant Kb is equal to ROL, right? Here the Kb is equal to ROL, Boltzmann constant, right? Is referred to as the Boltzmann constant. Right? That Kb is actually equal to ROL. Right, no? So I'll write the summary here. I'll write the summary here. So average for average kinetic energy, what we have learned now. Right? So two equations are there. One thing is kinetic energy per mole, that is 3 by 2 RT. Another thing is kinetic energy per molecule, that is 3 by 2 kBT. Right now? So these are the two expressions we have just derived. Right now? Okay. So this expression says that the, these are average, right? That the average kinetic energy only depends on the temperature. Only depends on the temperature. Right? Average kinetic energy only depends on the temperature. Right? Because 3 by 2 is a constant, R and Kb, the Boltzmann constant as well as the universal gas constant, those are constants. So Ek bar is proportional to T, only T. Ek bar is proportional to only T. So average kinetic energy only depends on the temperature. So basically you have to apply the absolute temperature here, the Kelvin temperature. So average kinetic energy depends only on the Kelvin temperature. Right? The thing is clear. So basically for these kind of gas systems, temperature means the kinetic energy. Keep that idea. Temperature means the kinetic energy. Temperature is a measure of kinetic energy. When the temperature is high, the kinetic energy is high. When the kinetic energy is high, temperature is high. Temperature is a measure of kinetic energy. Kinetic energy is a measure of temperature. Both way it is accepted, applicable. Right? In a gaseous system, temperature means the kinetic energy. Temperature is a measure of kinetic energy. Kinetic energy is a measure of temperature. Got that idea, right? So complete this note, Lama. Right? This complete this iteration, right? Right. First, write this thing, this part. Right? Then write this part. Right? Ultimately, just write this part. Right? Just complete the note. Afterwards, I will discuss more things about what we have derived. Just complete the stuff. Right, Lama? Which you have complete the note, right? Completed the note, right? So let's discuss the more important stuff we should know you should get from these expressions what we have just derived, right? So actually I have told you, just write those stuff. The major thing is average kinetic energy only depends on the absolute temperature. Actually won't depend on the pressure, won't depend on the other stuff, won't depend on the kind of gas, even won't depend on the kind of gas, right? So as long as both the gases are at the same temperature, the gas could be O2 gas, gas could be N2 gas, as long as both the gases are appearing at the same temperature, your average kinetic energy won't change. O2 gas at 300 Kelvin, N2 gas at 300 Kelvin, two gases but at the same temperature, average kinetic energy won't change. So average kinetic energy depends only on the absolute temperature, not changing according to the kind of gas. No capital M term appearing in these equations. If only capital M terms appearing, the molar weight term appearing, then only the stuff will depending on kind of gas. But in these equations, the capital N is not seen. So these two guys won't depend on the kind of gas, right? Won't depend on the kind of gas. So as long as you keep the temperature at a constant value, even with different gases, even with different number of moles, still you come up with the same average kinetic energy. That is the idea. Same average kinetic energy. Same average kinetic energy. Average. Remember that the kinetic energy will change, right? Kinetic energy will change with the amount of moles. Kinetic energy will change. The total kinetic energy of the gas system will change depending on the number of moles, but not the average kinetic energy. No N term appearing with the average kinetic energy. No moles term with the average kinetic energy. So average kinetic energy won't depend on the number of moles, but the kinetic energy of the gas system will. Right? Let's write those stuff, right? So we can write special note, right? Point number 1, average kinetic energy. Average kinetic energy. Now just write it with me, right? Write it with me. Average kinetic energy, the EK bar only depends on the Kelvin temperature. Average kinetic energy only depends on the Kelvin temperature, and keep that in mind, right? Does not depend on kind of gas. Does not depend on kind of gas. No capital M term appearing. Does not depend on kind of gas or even the number of moles. Right? So if you need some examples, right? Let's think of these examples. As far as you are keeping the temperature constant, the average kinetic energy is going to be the same, right? So see some examples. Some average kinetic energy of a N2 system. You have N2 gas appearing at 5 atm but kept at 298 Kelvin, let's say. Let's try to compare this thing with the average kinetic energy of some O2 gas, some different gas, right? At 580, sorry, at different temperatures, let's see, at 1080, but still kept at 298 Kelvin. Right? So what we can say is we have to only think of the temperature here, think of the Kelvin temperature here. As long as the temperature is kept constant, the average kinetic energy won't change. That is equal. Even though the two gas kinds are there, with even two different pressures, still as long as you are with same temperature, the average kinetic energy won't change. As long as you are with same temperature, average kinetic energy won't change per molecule as well as for the mole, right? No worries. Right? Let's examine another situation. Some EK bar for X gas. We don't know the molecule then. X gas, some X, right? Unknown, some unknown gas at 1080. Sorry, let's say some AAT and with 300 Kelvin. Let's compare this stuff with some EK bar of Y gas at BATA, some unknown ATM value at 400 Kelvin. So actually what I need to tell you is the temperature value. Knowing the temperature value is enough. Knowing the temperature value is enough to comment on the average kinetic energy. No need of knowing the gas exactly. No need of knowing the gas exactly. Which one was that? No need of knowing the pressure exactly. Just knowing the temperature will be enough to come up with the average kinetic energy. So you know, as here the temperature is high, right? Average kinetic energy should be high. As temperature is high, EK bar should be high with that system, right? Now, that is the idea, right? So let's complete these two. Small stuff, no? Right? The idea is clear, no? Right? So you can complete this thing as well, Lama. So just take the example here and let's write how this thing depends, right? So one can write that as well for a completion of note. When temperature increases, your EK bar increases, right? That is how it appears now. So with the use of this, we had came up with this, right? Greater the temperature, greater should be the average kinetic energy, right? Now? So that is what you should know with the second derivation coming from the molecular kinetic equation, right? Okay, right. So just complete this stuff, right? Just write in these two. Now I keep that in mind for any equation which is with the term R, right? The values, the numerical values should be applied with SI units, right? The numerical values should be applied with SI units, right? For any equation containing R, right? So if you are supposed to come up with the average kinetic energy with the use of this equation, or even if you are supposed to come up with the kinetic energy with the use of 3/2, right, nRT, still you have to apply all the values in terms of SI units. Then only you get the answer clearly and easily, right, in SI units as well, right? So even for the C squared bar thing, even for the earlier equation, what we have learned, the values should be applied with the SI units. The C squared bar we know, C squared bar is equal to, right, 3RTO M, no? There the M, the capital M, the molecular weight should be supplied in terms of SI units, which is the kilograms per mole. You have to substitute for the C squared bar equation for that capital M value in kilograms per mole, as SI units should be applied with the equations coming up with R term, use the gas constant, right? So keep that in mind, right? So you have some questions appearing in your workbook, this one, right? With your workbook, right? You have some questions, right? So with the molecular kinetic equation and the stuff, right? So in which page? So at the page number 11, at the page number 11, 12 and 13. At the page number 12, there is a nice question, the question number 19, right, which you are supposed to solve with the use of these kinetic energy equations. Not only these two, but also the kinetic energy equation, right? You may need to apply to solve for when solving the question number 19, right? So page number 11, 12 and 13 is with those questions are with theories regarding the molecular kinetic equation, right, and the theory, right? So just complete those things at home, right? So I'll send you the answers, right? I'll send you the answers. Just complete the stuff at home, right? Okay. After that, we are supposed to go towards the Maxwell-Boltzmann distribution, right? Our next discussion for today is all about Maxwell-Boltzmann distribution, right? So let's move towards that thing quickly, right? So we have to complete that thing as well for as today's lesson, right? So let's quickly go to that, right? Let's discuss about the Maxwell-Boltzmann distribution, right? Okay. Now we are going to learn about the Maxwell-Boltzmann distribution curve. Right, let's copy the Maxwell-Boltzmann distribution, right? That is the next topic, right? Okay, Maxwell-Boltzmann distribution, right? What this means, first thing, the Maxwell-Boltzmann distribution, what this means, right? So when we are discussing about the ideal gases, when we are introducing you the ideal gases, right, I had said that ideal gas molecules are traveling here and there, kind of random motions with different speeds. Random motions with different speeds. Not all the molecules are traveling at the same speed. If one molecule is traveling with the 2 ms minus 1, the other one will travel with the 5 ms minus 1, 10 ms minus 1, like that. So the guys are traveling with different speeds. So that speed distribution is actually discussed with this Maxwell-Boltzmann distribution curves. The speed distribution, the various speeds of gas molecules in your gaseous system, the distribution of speeds will be discussed here with the Maxwell-Boltzmann distribution curves, right? So at a note, it is said, see, according to molecular kinetic theory, we know that the gas particles, atoms or molecules travel in different speeds. The speed distribution can be shown as fraction of molecules traveling with the particle speeds shown below, and it is called the Maxwell-Boltzmann distribution, right? So basically, we can draw the Maxwell-Boltzmann distribution in two methods, right? We'll discuss both the methods, right? So let's see. So at the x-axis of a Maxwell-Boltzmann distribution curve, this is x-axis, right? It appears the molecular speeds. At the x-axis, you will see the appearance of molecular speeds. Normally denoted in ms minus 1, right? At the y-axis of a Maxwell distribution, Boltzmann distribution, it could be the fraction of molecules they are indicating, fraction of molecules. With considered speed, fraction of molecules with considered speed, or it could be the number of molecules with considered speed. Both kind of columns could appear in your papers, right? Number of molecules. With considered speeds. Right? At the x-axis is normal, right? It is molecular speeds. Right now? Okay. Let's discuss the appearance of these curves. Right? So the Maxwell-Boltzmann distribution curves normally appears like this, starting with here, somewhere going through along the x-axis, started like this, and coming up with a bill shape, bill shape actually with a right tail, bill shape with a right tail. It is not symmetric, Lama. It is not symmetric. It's not symmetric. It is a right tail. Right? So if you are to think like this, you clearly see some more space appearing here. Bell shape with a right tail. The right hand side you have tail kind of thing. That is how a normal distribution curve looks like, coming from the statistics, right? This thing will also appear like that. Bell shape with a right tail. Right? Right now? Okay, this is how Maxwell-Boltzmann distribution curve looks like. Right? Always starting from origin like this, but with going through the x-axis you are starting. Right? Okay, let's read this stuff. Let's try to read these curves properly. Right? To read these curves properly. Right. The first thing. Right? The idea is this. I'll give some explanation with this curve. we are the number of molecules with conserving speed appearing as the y-axis. Right? I'll give you the first description with this curve. Then we'll use those knowledge we have gathered from this curve to read the next curve, right? Okay, this one first of all. So actually, this thing, this dispersion curve, right, giving you an idea about number of molecules with a given speed, right? Number of molecules with a given speed, right? Or speed of molecules with the number of molecules with that speed, right? So the idea is this. See, I'll give you some idea here. So let's say I'll draw the one here. Now, first of all, normally the Maxwell-Boltzmann distributions are written for some considering the given temperatures, right? Let's consider it as 300 Kelvin, right? Maxwell-Boltzmann distribution curves are constructed for given temperatures, right? Okay, right. So the idea is this now. Let's say you are with some gas system like this, and few molecules are there, right? And say that you are with 3 molecules. See, this one, and this one. See, you are with 3 molecules, right? 3 molecules with say 10 ms minus 1 speed. Let's say you are with 3 molecules with 10 ms minus 1 speed, and let's say you are with 5 molecules with, say some 5 molecules are there, let's say with some 15 ms minus 1 speed, right? Let's try to read this one. So actually, at this speed axis, the speeds are marked. So the 2 speeds here are 10 ms minus 1 and 15 ms minus 1. So let's say the 10 is here. So the 15 is here. So this dispersion curve says with 10 ms minus 1 speed, see, you have how many molecules? You have 3 molecules. This is where 3 appears. With 15 ms minus 1 speed, you are with 5 molecules. That is the idea, right? So at the y-axis, number of molecules with the given speed. What is the given speed? 15 ms minus 1 for 5 molecules, 10 ms minus 1 for 3 molecules. That is the idea, right? So number of molecules with the given speed. So if you are referring to this kind of a speed, number of molecules with that speed will be given by, right? Will be given by this value, the value appearing here. If you are referring to this velocity, number of molecules with that speed will be given by here, number here at this axis. That's how we are supposed to read the curve, right? Okay, that is clear, right? If you are referring to this thing, this is all about number of molecules, easy to understand. But when it comes to this one, this is referred to as fraction of molecules. Fraction of molecules. Let's say altogether 100 molecules are there. Altogether 100 molecules are there. Altogether 100 molecules are there. So fraction means 5 molecules means as a fraction it is going to be, as a fraction it is going to be 5 out of 100, as 100 molecules are appearing, right? As a fraction, this is going to be as a fraction, this is going to be 3 out of 100, like that. Fraction means the number of molecules with the given speed divided by the total number of molecules. The total number appears as 100. If the total number appears as 50, then when taking the fraction, it is 3 over 50, like that. Fraction of molecules means the number of molecules of the given speed divided by the total number of molecules. So it can be represented as the number of molecules with the given speed divided by total number of molecules. In total, number of molecules with the given speed divided by total number of molecules. This is a fraction of molecules with the given speed. Right now, idea is clear. Right. So like the same manner, you can read this graph as well. So if I'm again take this as 100 for my easiness of calculation, right? So the fraction of molecules is going to be then 100 over 3 here and 100 over 5 here. So with the 10 ms minus 1 speed, this value representing here is then going to be 100 over 3, that means 0.03. With 15 ms minus 1 speed, value representing here is going to be 5 over 100, that is 0.05, like that. That is the idea. The fraction of molecules with a given speed, this is speed is 15 ms minus 1, you have 0.05 as a fraction. Fraction means the number of molecules with the given speed divided by the total number, right? So that is how we are supposed to read these two curves. Right? Things are clear. And few more stuff to learn. Few more stuff to learn about these curves. Let's discuss about those things as well. The two axes are clear now. Right. Let's discuss about the other stuff you should know about these two curves. Right? The other important stuff you should know. Right. 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 Next thing. ළමයි මේ few special speeds are appearing in these Maxwell-Boltzmann distributions. Some special kind of speeds. We have learnt about some special speeds now. Right? So when we are discussing about the molecular kinetic theory, we have discussed about some special speeds now. Remember that? Average speed, the root mean square speed, some special speeds now, right? How those things will appear at the distribution curve. Let's discuss about that thing. Where those average speeds will appear at this curve, right? Before coming to that thing, first I'll introduce a new speed appearing with the distribution curve, new kind of speed, that is this speed which I have marked here, the special kind of new speed, this value. What is this speed? So this speed is referred to as the peak velocity, C peak, the peak velocity, the speed related to the peak of the curve, speed related to the peak of the curve, peak velocity, right? In this curve as well, this speed referred to the peak velocity, C peak, right? The velocity which is related to the peak of the curve, peak velocity, C peak, right? And it is also referred to as the maximum probable speed. The maximum probable speed, Cp, is referred to as the peak velocity or the maximum probable speed. Peak velocity or the maximum probable speed. Let's discuss about this idea. What this maximum probable speed means. Lamai, this is the speed with maximum number of molecules. This is the speed with maximum number of molecules. So different molecules are coming up with different speeds, right? Say some molecules are coming up with 10 minutes minus 1, 15 minutes minus 1, right? Say out of these 100 molecules, let's say you are with some maybe 40 molecules with right kind of 20 ms minus 1 or something, and let's say this is the maximum number of molecules with a given speed. This is the maximum number of molecules with a one constraint speed, right? So that your maximum probable speed is 20 ms minus 1. So maximum probable speed is the speed with maximum number of molecules. The speed is maximum number of molecules. That idea is clear, Lama? So you see, right? Here is a situation where the maximum number of molecules are represented. With this curve, this is the point which represents the maximum number of molecules. These points, low number of molecules are there. With this point, even low number of molecules. The maximum number of molecules will be represented by this point. The speed related to that is the maximum probable speed. Speed with maximum number of molecules. Speed with maximum number of molecules is referred to as the maximum probable speed or the peak velocity. Right now? So keep that in mind. Speed with maximum number of molecules. Right? This is the speed with maximum number of molecules. Right now, that is the maximum probable speed which will appear with the peak. That is the speed related to the peak. Right now? Okay, that is very important. One important kind of a speed. Then let's discuss how the other speeds, what we have learned, the average speed as well as the root mean square speed appears there. We are not going to discuss about the mean square speed because this axis coming up with the ms minus 1, that is the unit used in this axis, ms minus 1, but the mean square speed appears as m squared s minus 2. So that can't be marked at this axis. What we can mark at this axis is the root mean square speed, which will appear as ms minus 1 again, right? So let's mark the two things, the root mean square speed and the average speed here, right? So basically the root mean square speed, may appear in this kind of a situation. Now give me a minute, right? The root mean square speed, right, appear in a position like this, which will be greater than the C peak, the root mean square speed, even in here, root mean square speed will appear at a greater side than the peak velocity. Root mean square speed, right? So if you are referring to the mean speed, mean thing will appear in between. The mean thing appear in between. So this is the mean. This is the mean. So mean means non average value will be coming up in between value normally. This is mean speed. Here as well, mean thing appears in between the peak velocity and the root mean square speed. Mean speed, right now. If you match that speed with the curve, you will get the number of molecules with that speed, right? Okay, that is how the speeds, the special speeds will be marked in these curves. Always the mean speed as well as the root mean square speed appears at greater speeds than the peak velocity or the maximum probable speed, right? That should be marked there. And then what else, the special things you should know about these two curves, right? The next special thing you should know is actually, before that I forgot that, right? So C peak actually, C peak is actually related to the root mean square speed, right? So the relationship is given in a note, right? So this C peak is equal to 0.82 of this thing, 0.82 of root mean square speed, right? That value is given in a note, right? No need to memorize this 0.82 thing, right? Anyway, what you should know is, as 0.82 stuff is kind of a constant, right? We can write the C peak is proportional to root mean square speed. C peak is proportional to root mean square speed. That means, most importantly, we can say the C peak is proportional to 3RTOM, because C squared by is the square root is equal to 3RTOM, the square root, right? So one can say C peak is proportional to TOM. Basically, these speeds are, these molecular speeds are proportional to TOM. Molecular speeds are proportional to TOM. When the temperature increases, molecular speeds will increase. As the kinetic energy, as the temperature increases means the kinetic energy will increase, no? That means definitely, right, speeds will increase. Kinetic energy increases means half m squared increases, right? Half m squared increases means as half and the m are constants for a given gaseous system, the mass of a gas molecule is constant, right? So for a given gaseous system, right? So as half and m is constant, the kinetic energy increases means velocity increases, right? So temperature increases means kinetic energy increases, that means velocity increases, speeds increases, right? So that is what it says, right? When temperature increases, definitely all the molecular speeds will increase, right? And m, weight, when the weight increases, right, velocities will decrease, that is what it says, molecular speed will decrease when the m increases. We'll discuss that in later, right, with more examples, right? So just have that idea. The molecular speeds are normally proportional to square root of TOM. Get that idea, right? That's all about the molecular speeds, right? Okay, next thing you should know, right, is actually the next thing you should know is about the area under the curve. That is a very special thing, right? Area under the curve. Area under the curve, right? Area under the curve. I'll write this thing. Area under the curve. in mathematics, right, there is a relationship called, if you are regarding these kind of xy curves, the area under the curve is equal to the summation of the y-axis. There is some, right, conclusion we made with differentiation. In mathematics, there is a concept called as differentiation, integration, differentiation, those stuff are there. No? So with differentiation, the scientists have proved for xy curves, area under the curve represents the summation of y-axis. What is that idea? The point is this. What is the area under the curve? Right? I'll write it here. So yeah, I'll write this point is here, right? So if you are with kind of xy curve and you have a curve like this, so this is the area under the curve, this is the curve. So if you are taking the area under the curve, this is the area under the curve, right? With differentiation in mathematics, we can prove that this area under the curve, area under the curve, area under the curve is equal to, so this is the curve, this is the area under the curve, area under the curve is equal to summation of y-axis. There is such a relationship, right? Say it's like this, right? If you take like this, right? Say this is the match and this is the runs that Kusalmindis had, right, made. Say this is the number of matches. First match, Kusalmindis got this kind of run. Second match, Kusalmindis got this kind of run. Third match, he got this kind of runs, right? So this is the matches versus runs. So that means this is the x-axis, the y-axis. No? So if you are able to come up with the area under the curve, that will give you the summation of the y-axis. So if this kind of curve is there with the Kusalmindis performing, right, the area under the curve, this area will give you the total runs. Kusalmindis had collected. That is the idea. Area under the curve gives you the summation of y-axis. Right? This is number of matches, and the runs he got. If you think of Kusalmindis, normally, right, his curve would be like this, right? His curve would be, right, most probably like zero runs with more matches, no? 0 runs with more matches, right? Like this kind of curve Kusalmindis could have, right? More matches with 0 runs, right? Anyway, right? The area under the curve will give you the total runs of Kusalmindis, right? 0 runs more matches with Kusalmindis, right? Okay. Anyway, so that is the idea. For any xy curve, the area under the curve will give you the total of the y-axis. The idea is clear, right? So let's apply the stuff to these two curves, right? So if you think of the area under the curve for this curve, is the area under the curve. This is the area under the curve, right? So this area under the curve is actually equal to what? Summation of y-axis. So we can say the area is equal to summation of y-axis. This is the summation. So number of molecules, summation of number of molecules, that is total molecules, total number of molecules. That is what represented by the area under the curve, which is with the y-axis with the number of molecules with considerable speed. Number of molecules, the total, will be determined by the area under the curve, right? If you think of the area under this curve, area under this curve, area under this curve, the summation of y-axis. So this is about fraction of molecules, fraction of molecules. So summation of a fraction will give you 1. Summation of a fraction will give you 1. So area under the curve representing 1 in this curve, fraction of molecules is considering speed. If the y-axis is like that, so your area under the curve will give you 1 unity. The summation of fractions will be equal to 1. Right? Those things should be also known to completely examine these curves, right? So this will be important for our next discussion, right? Okay, mark those things as well, right? So those are the 2 Maxwell-Boltzmann distributions, right? Okay. So let's move to the next section, right? Let's move to the next section, right? Now we are going to discuss about how these curves will vary with the temperature changes as well as with the change of type of gas. The kind of gas as well as with the temperature changes, let's discuss how these curves will vary. And you should definitely know, right? As now we have learned that molecular speeds will depend on TOM, as we have learned the molecular speeds are proportional to the TOM. Definitely when the temperature increases, the molecular speeds should increase, as well as when the molecular weight decreases, the speeds will increase, right? So according to the temperatures and the kind of gases you are using, the molecular speeds will vary. Some changes could be seen. So variations could be seen with the 2 curves, depending on the temperature you are using as well as the kind of gas you are using with the gaseous system, right? So let's discuss about that, how these curves are supposed to vary depending on the temperature changes as well as change in gases, right? Okay, let's come up with that. Right. So first let's discuss how these curves will vary with the temperature, right? Variation of Maxwell-Boltzmann curves, right? Depending on the temperature, right? Okay, let's discuss this concern kind of a Maxwell-Boltzmann distribution curve written for N2 gas, some gas, same gas. So here molecular speeds appear At here I'll copy the fraction of molecules, right? Normally fraction of molecules is the axis we are dealing with the areas, right? Frequently. With considering speed. Right? Okay. Let's discuss how these molecular speeds, how these things will vary with the temperatures. So I am concerning the N2 gas, some constant gas with two different temperatures, right? With two different temperatures, right? Say if you had done the experiment with two different temperatures and observed some variations like this, and observed some variations like this. Right? You had done the experiment concerning two temperatures, right? Let's say the two temperatures you have concerned is actually one is 300 Kelvin, the other one is 600 Kelvin. Concerning two different temperatures, let's say you have done two experiments, right? Let's discuss about the Maxwell-Boltzmann distributions here. So we are supposed to come up with the correct curve with the correct temperature. We are supposed to match the correct curve to these temperatures. So what is the curve which is related to 300 Kelvin, and what is the curve which is related to 600 Kelvin? So I'll ask you a question. What is the right curve which is related to 600 Kelvin? What is the curve which is related to 600 Kelvin? What is the curve? How to come up with an answer? Let's see how to think of this. It's like this, Lama. So few ways of looking at this thing. First of all, Lama, we know that the molecular speeds actually are proportional to T over M, the square root, right? The T over M square root. The molecular speeds are proportional to square root of T over M, right? So as long as we are dealing with the same gas, right, the molecular speeds will depend only on the temperature there, right? So we can use this thing to find out the correct curve. See, how can we use this thing? So if you are thinking of the blue curve, it's C peak appearing here, peak velocity. If you are regarding the red curve, it's C peak appearing right at this point for the red curve, maximum roller speed, right? According to this thing, it says when temperature increases, the molecular speed should decrease. Molecular speed should increase. So the greater molecular speed should come up with the higher temperature. So that greater C peak should come up with the greater temperature. So you clearly see the greater C peak appears here. So C peak is a speed, right, which will appear at the speed axis, right? C peak is a speed which appears at the speed axis. So greater C peak is this one, right? The C peak of red thing is greater than the C peak of blue thing, right? So that should be the one with a greater temperature. Greater the C peak, greater the molecular speed, greater the temperature. So this should come up with the 600 Kelvin, and the smaller one should come up with the 300 Kelvin, right? So the red curve is the one with the 600 Kelvin, so that blue curve is the one with the 300 Kelvin. That is how we are supposed to, right, label the curves. Right now? Now don't confuse with this height, right? This height represents the number of molecules. This height won't represent a speed, right? The height represents the number of molecules with given speed. Number of molecules with given speed, the height represents. Or the fraction of molecules with the given speed, that is what height represents. The speeds are represented here at the speed axis. So you have to look at the speed axis. The value appearing at a greater value, the Cp appearing at the greater side of the speed axis is coming up in the greater temperature. Right? Okay, that is the idea. So you can use this equation to label the two curves. Or another way of looking at the same problem, right? Or one can think like this. So basically, we know that when the temperature increases, the kinetic energies will increase. So temperature means the kinetic energy, right? Temperature means the kinetic energy, right? We know when temperature increases, kinetic energy increases, right? So it's like this, no? So kinetic energy, right, means this thing, kinetic energy proportional to temperature, right? And we know when the temperature increases, kinetic energy will increase, right? So I'll write it like this, right? So the temperature increases, kinetic energy will increase. Temperature means the kinetic energy, right? Okay. On the other hand, we know the kinetic energy is equal to half mv squared. As temperature increases, kinetic energy increases. That means this whole term should increase. As m is a constant, as all the particles are into, as m is a constant, this should appear by increasing velocity. This could be done only by increasing velocity. So when the temperature increases, the curves should shift to higher velocities. When the temperature increases, the curve should shift to higher velocities. So that is what we see. When the temperature increases, the curve shift to higher velocities. Shift to the right. Higher velocities means going towards here means higher velocities. Shift to the right. Curves shift to the right. Right? So I can say neither. When temperature increases, curves shift to the right. Shift to right. Right now? So we'll write those things as well. Right? This is what happens with the increasement of temperature, right? I'll write it like this. Right? I write the points as well. What are the two things happen? Right? Curves shift to the right. Curves shift to the right means higher temperatures, higher velocities. Higher speeds. That means right. Curve shift to right. Right. What is the other thing happens? Let's discuss about this special point as well before writing. Right. Curve shift right. When this curve shift to right, very important thing to note here. Right. Let's say what happens to the number of molecules with smaller speeds and what happens to the number of molecules with greater speeds. So with this, right, number of molecules or fraction of molecules right with low speeds. Let's discuss what will happen to the low speed situations and with high speeds. Let's say, see what will happen. So number of molecules with low speeds. So this is a low speed, right? I consider here low speed. So number of molecules with low speeds. See, number of fraction of molecules with low speeds. See what will happen. When the temperature increases, the curve, the blue curve shifts to the red curve. No? That means when temperature increases, the number of molecules with low speeds, earlier it was this number, now it is this number, right? With a low temperature, number of molecules with low speed, this specific low speed is this amount. With a higher temperature, the number of molecules with this speed is this amount. So number of molecules or the fraction of molecules with this speed has decreased when you increase the temperature. Decreases when you increase the temperature. Right? What about the number of molecules with high speeds? See, I'll take a high speed like this. This is a situation with high speed. See, the fraction of molecules or the number of molecules with high speeds. What happens there? So with the low temperature, only this amount of molecules with that high speed at low temperature. At a higher temperature, this amount of molecules are with this speed at higher temperature. So at a lower temperature, only this amount of molecules with this speed. At a higher temperature, this amount of molecules with this speed. So the amount has increased. So number of molecules or fraction of molecules with high speeds will increase from here to here. So that is what happens. This is what happens. This idea is very clear, am I right? When you increase the temperature, kinetic energy increases. That means the speeds of all the molecules will increase. The curve shifts to the higher speeds. When the speed of all the molecules increases, now even the molecules earlier with small speeds now are with higher speeds. All the molecules have increased their speeds now. As the temperature increased, all the molecules have increased their speeds. So that the molecules which travelled with small speeds earlier now will travel with high speeds. So number of molecules with lower speeds now decreases. Most of them now travel with high speeds. So number of molecules with low speeds decreases. What happens to number of molecules with high speeds? Now even the molecules which were with small speeds earlier now came to the higher speeds as the temperature is increased. Now some more portion is introduced towards higher speeds as the temperature is increased. So now you have more molecules with higher speeds than the situation with a low temperature. That is why we say number of molecules with high speeds will increase with this effect of increase in temperature. Right? So the thing is clear. So just draw this stuff, Lama. Just draw this stuff and complete the thing. Quickly draw, Raman. Right. Let's complete the next one as well before winding up the class. Right. Complete the effect of the kind of gas as well, the molecular weight effect. Right. I'll come up with the same kind of thing, two graphs, right? I'll draw the same thing right here. Same two kind of graphs, right? Right. See. Right. Let's apply the same theories for variation of Maxwell-Boltzmann distribution curves depending on the molecular weight here. Given the molecular weight here. Right. So when molecular weight increase, let's see what will happen. So let's take two curves with two different gases, one for O2 gas, let's say, the other one for N2 gas. Both are at the same temperature. Let's consider both are at same 300 Kelvin temperature, same constant temperature. One curve representing the O2 gas, one curve representing the N2 gas. Right? We need to label the two curves. We need to label the two curves. Right? Okay. Right? Right. Okay, let's apply the theories here. When molecular weight increases, what happens here? When you increase the molecular weight, molecular speeds will drop. Molecular speeds will drop. When you increase the molecular weight, keeping the temperature constant, the molecular speeds will drop. I'm considering the O2, right? O2. This guy is with 32 now. This guy is with 28 now. So if the molecular weight is high, molecular speeds are low. Molecular speeds are low. So oxygen should come up with the smaller speed. Molecular speeds are low. So this is the one with the smaller speed. Out of the two C peaks, This is the one with the smallest speed. So this should come up as the O2. Cp equal 4 right? When the molecular weight is high, that guy's molecular speeds are low compared to the other. So C peak should be low compared to the other. So the O2, the blue color one is the O2, and the red color one becomes the N2. Right now? So with use of this theory, you can label the curves. Or else you can use this thing as well. As you are keeping the temperature constant, Ek should be a constant. Ek should be a constant. So that this term should be a constant. As you are keeping the temperature constant for both the O2 and N2 gases, is the N2, both the N2 and O2 gases, as you are keeping the temperature constant, the average kinetic energy won't change, right? Average kinetic energy depends only on the temperature, right? That won't change. So this should be a constant, right? So then, if your weight of the particles are high, keeping this whole thing a constant, the velocity should decrease. To keep this whole thing a constant, if your weight of the particles are high, the O2 molecules are heavier than the N2 molecules. If the weight of the molecules are high, your velocity should be lower to keep this thing a constant. Right? So the curves should shift to low velocities. When the molecular weight increases, right? Curves shift to low speeds. That means shift to left. Low speeds means shift to left. Right? So when those curves shift to left, that means going from N2 to O2, when those curves shift to low speeds, now the molecules earlier with greater speeds are now with low speeds. When the curves shift to low speeds, when the molecular weight increases, as curves shift to low speeds, now the molecules which were with high speeds earlier, now with low speeds. Now you have more molecules with low speeds then. Because the molecules earlier with higher speeds also now coming up as molecules with smaller speeds. So now you have greater amount of molecules with low speeds. What about the other thing? Molecules with high speeds. So as curve shifts to the left, right? Now as curve shifts to the left, now the molecules with higher speeds became molecules with low speeds, because curve shift to the smaller speeds. Earlier the molecules with greater speeds, now coming up with smaller speeds. So the molecules with higher speeds decreases. Those things converted to lower speeds, so molecules with higher speeds decreases. So that can be seen, right? So when the molecular weight increases, right, coming from N2 to O2, molecular weight increases. Earlier this much of molecules were there with the higher speeds, now this much is there. The amount decreased. Right? Thing is clear? Right. Just complete this stuff, Lama. Just complete this thing quickly. Right. Okay, the final thing you should know is, now when writing these Boltzmann curves, right, there is some pattern there. There is some pattern there. There is one pattern. What is the pattern? Now, when you are shifting these curves, which I'll tell you like this, when you're shifting the curve to right, some special thing should occur. What is that? This height, if you're supposed to shift the curve to left, towards higher speeds, what happens to the peak? The peaks will also shift to right and down. Remember that. When you are shifting your Boltzmann curves to higher speeds, that is what happens when you are shifting from O2 to N2. When you are shifting your Boltzmann curve to higher speeds, what actually happens is your peak of those curves will also shift to right as well as down. The reason for that thing is to maintain the area under the curve a constant. That should be equal to 1, right? That should be equal to 1 because the area under the curve should give you the summation of y-axis, that is equal to 1 here. So to keep the area under the curve a constant, when you shift the curves to right, always the peak will shift to right and down. Keep that in mind as well. Write that thing as well. Right? Okay. So that is all you should know about the Maxwell-Boltzmann distributions, and with this, let's wind up for today's session. Okay. So let's meet at the next day's class next week. Until then, goodbye.